in our group, we touch both aspects of data interpretation. We work a lot with hyperspectral data, also with other kinds of remote sensing data, but we also have an interest in trying to have the analysis or the extraction of information conducted in a time that is sufficiently relevant for the applications that we are exploring. And in some cases, these applications require a response in real time or in near real time. So I think that there's still a challenge on how to exploit remote sensing data in a way that is useful to society, because normally remote sensing data are very huge. We have multi-temporal data, we have high dimensional data, the temporal, the spatial, the spectral resolutions are ever increasing. So there is a problem on how to analyze the data, how to store the data, and how to efficiently operate with the data. So that's why the focus on this course will not be so much on the information extraction part as on the high performance computing. Anyway, I will try to mix both aspects in the presentation. I also wanted to say, if you feel like asking questions during my talk, it's okay. We don't need to wait until the end for the questions to be asked, because I will keep an eye on the panel, on the Q&A panel. So feel free to interrupt me during the presentation. I will read the panel and I will try to reply to questions online at the same time as the questions pop up. Okay, so I'm going to start by giving you a summary of the tutorial. First, I will talk about some computing requirements for remote sensing applications. Actually, I will start with a very brief and very general introduction about remote sensing in the optical domain, because we have other speakers covering the other domains. After this brief introduction, I will talk a little bit from an introductory point of view about parallel processing, what means to process data in parallel, and how we can optimize the computing by parallelizing tasks. For that purpose, I will also describe several data partitioning strategies that can be applied not only to hyperspectral, but also to other kinds of remote sensing data. And then I will particularize on different kind of architectures. As you probably know, clusters are the most traditional way to perform parallel computing. It's basically connecting computers together using a communication network. Sometimes the clusters are heterogeneous because we have different kind of processors, even different kind of communication networks. So there are some challenges on adapting processing algorithms to this kind of architectures, because we need to take into account the processing speed of the computers, also the velocity of the network in transferring messages. So I will talk a little bit about how to adapt algorithms to heterogeneous systems. And another important component of the tutorial is how to perform parallel processing in specialized hardware devices. Here we will be talking mainly about FPGAs, field programmable gate arrays, and GPUs, graphic processing units, which are now the two main kind of hardware architectures that you can find on board the instruments that are currently being used for Earth observation. Now, the advantage of these devices is that you can conduct the analysis in real time. That means that you are analyzing the data at the same time as the data are collected. So this is quite important in some specific applications, although there are still some challenges about real-time, fully real-time data processing. So we will be talking a little bit about this in section number 5. In number 6, I'm going to talk about other parallel processing strategies. I'm sure a lot of you are dealing with big data, deep learning, all these new or recent strategies for data processing that are very efficient in remote sensing data analysis. So I'm going to talk a little bit about frameworks for deep learning, and also about strategies for big data analysis using tools like, for example, Hadoop, Spark, which are particularly useful for distributed data processing. Then at the end of the tutorial, in point number 7, I'm going to describe an application case study. I have selected hyperspectral mixing, which is one of the particular ways to exploit hyperspectral data that you cannot find in other kinds of data, like, for example, radar data or even multispectral data. So in this case, we are going to take advantage of the high spectral resolution of the data to overcome the limitations of the spatial domain. That means we use the spectral resolution to see a little bit further than the pixel size, and we can perform some kind of analysis at the sub-pixel level. I will describe the techniques that are available for this, and then I will introduce several different parallel processing strategies using different high-performance computing architectures, and we are going to do some comparison. I will point at some data sets that you can use, and you can basically try by yourselves some of the examples that I will provide in this section. And then I will conclude with some summary and future directions. As mentioned, I hope we can do this interactive, and please feel free to provide questions while I'm providing the presentation. I see that there are already some comments, but not really questions. So I'm going to start with section 1, computing requirements in remote sensing applications. Okay, here you can see a very schematic, very general way to describe what is remote sensing image processing. Particularly, we are talking about the acquisition of data here. As you can see, there is a sensor that is collecting data about the Earth without actually physically taking a sample of the surface. So that means we are collecting the data remotely. And this sensor can be mounted in different kind of platforms. We will see later, usually we see satellites or airborne instruments, but you could also have a drone or a more commodity, to say so, platform. The idea is to have a kind of camera or a kind of sensor to measure, for example, in optical data, we measure the energy reflected from the Earth. Normally, and in this course, we are going to basically assume that most of the time, this information can be arranged in the form of a matrix of digital values that can be displayed as an image, as a digital image. And then normally, even if we have a grayscale or multispectral or hyperspectral image, depending on the number of bands, on the number of matrices that we are going to process at the same time, we are going to perform some kind of information extraction from the data. So generally the key about how to analyze the information that we have in the data. And from this information, we are going to perform some kind of interpretation and hopefully address several applications that can be related with many different topics, from atmospheric science to land use, geology, hydrology, agriculture, mineral exploitation, soils, or even disaster monitoring. Depending on the temporal resolution, we can even perform multi-temporal assessment. We can, for example, analyze how agricultural fields or forestry are evolving in a certain time period, or what has been the impact of urban development on a certain area. So we have many possibilities with this imaging acquisition and interpretation process that I illustrated in this slide. Of course, the kinds of remotely sensed data sets are very different. And in this tutorial, I'm just focusing on basically optical, multispectral, hyperspectral data. But in other tutorials of this summer school, we will see information about how to process radar data, synthetic aperture radar, microwave data, or even other different kinds of data. So in general terms, there is also a very good opportunity for fusing all these kind of data sets to address different problems. And I would like to emphasize that different kinds of data have some advantages and disadvantages in different contexts. So somehow it is generally a good idea to exploit them in simultaneous fashion. Also, these days, there are many people who are trying to use other sources of data, not even related with remote sensing instruments, but for example, social media data, or even texts that are available in different applications to combine and to provide a conglomerate of data that can be exploited in different applications. But again, the focus on this course will be mainly on optical and particularly multispectral and hyperspectral data. So here you have some examples of remote sensing applications. Like for instance, in land, we can analyze rocks, minerals, faults, land use and land cover, vegetation, digital elevation models, snow and ice, urban growth, even environmental studies. So it's really a wide range of things that we can do with remote sensing data. For oceans, we can also analyze the color, the temperature, the winds. And there's also a very important part related with atmosphere, like how to estimate temperature, precipitation, clouds, aerosols, and so on. Now let's focus a little bit more particularly on optical remote sensing. And in this slide, you can basically see the different applications that we can have. As you can see, this is strongly dependent on the spectral resolution of the data. So the idea is that basically depending on the number of bands, the number of spectral bands, we can have a more detailed way to interpret and to discriminate the information coming from the data. So mainly talking about optical data, we can go from simple panchromatic data, that means color images, to multispectral with tens of bands, hyperspectral data with hundreds of bands, and ultraspectral data with thousands of bands. According to the spectral resolution, let's say you can do more complicated things. So for example, with the basic spectral resolution, you can do detection. That means we can identify the presence or not of a given material, object, or activity. According to the number of bands, if we have more bands, if we have more spectral resolution, we can do more complicated things. For example, we can do classification. Classification means separating materials into spectrally similar groups. For example, if we want to do urban data classification, we can separate between, let's say, one kind of roof and another, roads, cars, and different kind of construction materials, for example. So this is something that is normally facilitated by the increase in the spectral resolution. If we have more spectral resolution, we can do discrimination, like determining categories of the classes. That means we are more precise and more accurate in the classification. If we have more spectral resolution, we can do identification. That means we can determine the unique identity of the generic categories of classes, for example, for land cover or mineral mapping. We can also do characterization. That means determining the variability of an identified material, and that is also related with the availability of multitemporal information. And I like to put this technique at the top because it's generally the most complicated and the most tailored to the number of spectral bands, which is spectral unmixing or spectral mixture analysis. That means we can determine not only the presence, but also the abundance of materials. For example, in precision agriculture, we can determine how much of a given crop is present at a subpixel level. We don't need to have a tremendously fine spatial resolution, because with a mixing, we can see beyond the spatial resolution of the pixels of the data, and we can determine what is the fractional coverage of the main classes. These are the so-called end members in the hyperspectral data. So we have an end member would be a kind of spectral signature that is pure, and in the unmixing, the idea is to determine what is the fraction of each end member in the mixed pixels that we have in the data, which eventually are most of the pixels because of the limited spatial resolution. This is something that we are going to discuss also later, because normally when we have high spectral resolution, the consequence, because of the optics of the instrument, is that the spatial resolution will be not so fine. So there are some challenges in balancing the spectral and the spatial information, particularly when we do spectral unmixing. Okay, so here you have a very basic representation of a multispectral image. As you can see, the main difference with a grayscale image or a single matrix of data is that we have several bands. Normally the bands are associated to different wavelengths, different portions of the electromagnetic spectrum. So a pixel is no longer a single digital value, but we have a multispectral or vector-based pixel value, in which the pixel collects different values per band. So if we put together all this information, you end up with pixel vectors that of course increase the computational complexity of the data that you want to process. So the multispectral image has 3 dimensions. We have lines, samples, that means the spatial dimensionality of the data, how many pixels we have. And actually in the spectral domain, what we have is a number of bands that is related to how many spectral bands we have in the data. Okay, I can see the question. What is exactly means band here? Okay, this is basically what when we talk about band, we are talking about information in different parts of the electromagnetic spectrum. For example, one band could be in the visible part of the spectrum, but according to the resolution of the sensor, maybe we have also the possibility to collect data in the near infrared part of the spectrum, or in the even in different portions in the thermal part of the electromagnetic spectrum. So the meaning of band is we have an image, but the image is associated to a given wavelength, to a given spectral value. So this band over here in yellow would be collected over a different part of the spectrum, over a different wavelength than this one here in green, because you know, the amount of energy reflected in one band and another would be different. So in this case, the concept of band is strongly associated to the spectral resolution of the sensor. The more the spectral resolution, the more bands we can have. And actually this allows me to link very well with the next slide, which shows you, for example, how we can store this information in multispectral data. Here we have a band that is covering a portion of the near infrared spectrum from 750 to 900 nanometers. This is the red band, which is related to a different portion of the spectrum from 640 to 690 nanometers. And this is the green band from approximately 525 to 605 nanometer. How we store this information? We still keep the same matrix representation, but we need to store different bands in order to comprise, to collect all the information that we have as recorded by the imaging instrument. In each of the bands, we can use a certain amount of bits, a certain radiometric resolution, in order to represent the information that we are storing. So for example, in this case, we are using 8 bits to codify each pixel in the different bands. So if we use 8 bits, that means that the lowest value that we can use is 0, which is black, that means no reflectance. And the largest value would be 255, which is basically the maximum value that we can obtain by using 8 bits codification. So in this case, 255 would be white color. And in the middle, what we have is different kind of grayscale values. So in this case, according to the question, the band concept is not related with polarization. It's mainly related with the amount of energy that we can collect at that particular region of the spectrum, of the electromagnetic spectrum. So what we are doing is to try to represent the amount of energy, reflected energy, that we are collecting by the optical instrument at different wavelengths. And we use one different matrix per wavelength or wavelength region that the sensor is able to analyze or to collect or to record information. There are some sensors that are only collect information in the visible part. For example, in that case, normally multispectral images do not provide information in the thermal part of the spectrum, so to say. So that also depends on the ability of the sensor to collect data in one particular wavelength or a different one. According to the way to store this information, we can use different formats. And in the slide, I'm showing 3 of them: BSQ, which is band sequential; BIL, which is band interleaved by line; and BIP, which is band interleaved by pixel. So in band sequential, we have a long file in which first we put one band, like this band here, one pixel after another. Then we codify the second band, and then we codify the third band, and so on. So that means bands go one after another. In BIL, band interleaved by line, basically we store first the first line of the first band, then we put the first line of the second band, and then the first line of the third band. Then the next piece of information is the second line of the first band, then the second line of the second band, and then the second line of the third band, and so on. So in this case, the processing favors the interpretation of lines, because we will find consecutive lines in the file that we are using to store the multispectral data. And finally, my favorite format for hyperspectral data analysis is BIP, band interleaved by pixel. That means first we store the first pixel. We take the first pixel value of the first band, then we take the first pixel value of the second band, and then we take the first pixel value of the third band. That means we are storing consecutively all the values of the pixels so that we can analyze better the spectral information associated to the pixel. That's quite important because, as you will see later, the main information that we care about in hyperspectral data is the spectral signature that is associated to the pixel, because that signature will give us some very detailed information about the objects and about the materials that we are observing. So it makes sense to have these pixels consecutively stored in the file, in the format, in order to facilitate the processing. And sometimes even without doing any kind of parallel processing, if we use the right format for the right algorithm, it will tremendously impact the processing time, because, as you know, hyperspectral images are very large and sometimes cannot be completely stored in the cache memory, of course, and even in the main memory of the computer. Maybe they will not fit. So sometimes we need to use a lot of access to disk, to secondary memory, and that has a lot of cycles, that has a lot of delay. So yes, Lodere has a question related to the metadata of the images. Yes, for example, if you use an MB file, you will see in the beginning that there is a line in the header file or in the metadata telling you what kind of format is used to store the data, and then you know exactly how to read the file based on the metadata. So that's a very good question. Why isn't processed panchromatic band of Landsat to surface reflectance? Well, this is kind of related to the processing, and I'm not really sure about that, but I guess it's related to having all the information collected by the sensor. In this course, we are going to focus on hyperspectral data mainly. So I'm going to move on to the concept of hyperspectral image. And in this case, you will see the concept is strongly related, not to the way that bands are particularly processed, but to how close the bands are, and to particularly how many bands we have in the data. So this paper was published in 1985. As you can see, the idea of hyperspectral is not new. is basically something that we have been talking about for many years. But I truly believe that we have arrived to a point where hyperspectral data are becoming really useful in this particular case because of the many applications that that are used to exploit hyperspectral data. And regarding the question of Mansour, the format is not related to the codification, I guess, of DM values. No, the format is related to how we store the information or the pixels that we are collecting by the instrument. The digital number is related to the radiometric resolution. That means, for example, if we are using 8 bits, we can use 255, 256 values to codify the reflectance information. If we use 16 bits, we can use more values. So that's what impacts the codification of digital numbers, the number of bits, which is related to the radiometric resolution. But with different formats, you can have the same radiometric resolution. BSQ, BIL, or BIP, all the three of them can have the same radiometric resolution. So there are different things. One is related to how we store the pixel data, and another one is how many values are we going to use to codify each pixel value or each measure of energy collected by the instrument. Okay, one thing I wanted to point out, coming back to the concept of hyperspectral image, is there are two important things. One is we should have a large number of bands. You can see that in this paper in Science, Alex Getz, who is widely regarded as one of the fathers of hyperspectral imaging, he was talking about a large number of bands. He was talking about more than 40. Now we have hundreds or even thousands. But one important concept is narrow bands. This is a very important idea, and I would like to, emphasize this particular word, this narrow concept, because basically I believe it's more important for hyperspectral to have narrow bands that are very close in width, almost contiguous, rather than the number of bands. Because this idea of having bands that are particularly close one to each other allows us to have a kind of contiguous spectrum. Contiguous in the sense that the spectral signature can provide a very good representation of the objects that we have in the data. So this contiguous thing is another very important keyword. Okay, I think I lost my pointer. But yeah, I want to emphasize the word contiguous there, because in the end, the key aspect about hyperspectral imaging is that to see spectral signatures that closely relate to the materials that we are observing, and somehow we can obtain information about the biochemical composition of these materials. That's why a mixing is also very important, because by looking at the spectral signature, we can be automatically able to determine if some material that we are observing is appearing in pure form, that means we have an end member, or something is mixed by different end members. In this case, hyperspectral data allows us the possibility to unmix the pixel. That means we can determine how much of an end member is present in each pixel of the data. Okay, so we are going to move on, and I think I need to fix this problem with my pointer. Sorry about that. I'm going to try to remove this bar over here, because otherwise I cannot. I cannot pass the slides. Okay. Now I think it's working. Okay, let me remove this thing over here. I'm not sure if you are seeing this. I don't know, something messed up with my presentation, with the annotation. Okay, so with hyperspectral images, as mentioned in the previous slide, we have two main characteristics. One is the high dimensionality in the spectral domain with hundreds of or thousands of bands. Another important characteristic is the bands are almost contiguous. So these two properties are fundamental. And then resulting from these two properties, we have the fact that each pixel provides a spectral signature. And a spectral signature is a very accurate representation of the materials that we are observing. So if we look at the concept of grayscale, color, and hyperspectral, you can see that these three concepts are pretty much defined by the number of bands that we have available. In grayscale images, we have one band. We can use a radiometric resolution of 8 bits, 16 bits, even more. So we will have a different range of digital numbers. Then we have a color image. In this case, we have three bands, and for each band, we have a certain codification that depends on how the reflected energy interacts with the wavelengths at different parts of the spectrum. And then with hyperspectral images, we have a notoriously larger dimensionality with very narrow, very close bands to each other. So if we put together all the information that is collected for a given pixel, we have a very fine, very detailed spectral fingerprint of the materials that we are observing. Let me give you a very simple comparison. We are comparing Landsat data with a hyperspectral instrument. One of the reference instruments that we have in our community is called AMERSIE. And recently there has been a new generation, AMERSIE NG, which is now collecting data, and we are quite excited about this new evolution of average. But you can see the classic average collects data from approximately 350 to 2,400 nanometers. So the sampling, the number of measures collected by a hyperspectral instrument, is much more detailed than the number of measures that are collected by a multispectral instrument, even if in this particular case, the wavelength or the sampling in the spectral domain can be quite similar. But the difference is we can see much better the objects with the hyperspectral instrument because we have a much more detailed spectral resolution. So that provides the possibility to better model the spectral response in the wavelength range. And one important thing is that the increase of spectral resolution usually comes at the expense of spatial resolution. Fortunately, we have techniques such as mixing that allows us to overcome this problem. But another, very important conclusion that we can make from this figure is that we are going to need much more significant computationally and storage requirements in order to deal with hyperspectral data rather than to deal with multispectral data. So not only we have more resolution, more information, we have more detailed spectral signatures, but we have a more challenging way to do things in the sense that we need to store the data. Even if we process the data, we need to keep it in the memory of the system, and sometimes we will not be able to have it in the main memory. So we need to resort to the secondary memory that is much slower than other parts of the computer. So there has always been a computational aspect associated to hyperspectral data. Probably that's why we see very small data sets when we read papers about new techniques. Normally we see very small, very reduced benchmark data sets that are recurrently used for validation, but it's very strange that we see papers with really large hyperspectral data. That's because somehow in our community we are used to simplify the computational requirements by reducing the size of the problem. But in reality, if we really want to exploit hyperspectral data to the full possibilities that we can obtain from that kind of data, we should be able to process large data sets. And this slide also gives you an idea about spectral continuity. If we want to single out the most important distinguishing feature of hyperspectral data, is that somehow the spectral signatures can be considered almost continuous due to the very narrow separation between these bands in the electromagnetic spectrum. If you look at the broadband spectrum in Landsat, it's completely different story. The picture is completely different. With the image in the bottom, with the spectral signature that we can see in the bottom, we can understand much more about the object that we are observing rather than with a more simplified spectral signature, as we can see in the top. So for the computational requirements, there are many different ways that we can think about this, because of course we can decide about many different kinds of high performance computing architectures to process the data. As we know, the sensor collects the data in many spectral bands, so that each pixel is a combination of the reflected or emitted energy from all the features that fall within that pixel area. And if you put together all the information provided by a pixel vector, you have a full spectral signature or fingerprint that normally is unique or gives you a unique interpretation of the materials that you are observing. If you increase the spectral, spatial, and temporal resolution, you end up with massive data archives and hyperspectral data that are huge in terms of volume and dimensionality. So it really depends on the kind of application that you want to address. There are different kinds of high-performance computing infrastructures that you can use, and I already mentioned clusters, for example, are the traditional way to exploit hyperspectral data. But in this particular case, for a cluster to be useful, you need to wait for the data to be sent to Earth and to be processed. So in certain applications, this is not good enough, because imagine a case like the one I'm showing here. This is the average image that was collected after the World Trade Center terrorist attack in 2001. It's a pretty old image, but it has become a benchmark in high-performance computing, mainly because the data were not useful at the time of data collection. There were many images collected over the World Trade Center site, and the idea was to be able to use the data to locate the fires and to identify the hotspots in the area. But at that time, 2001, there was not really a capacity to process this data in real time. So there were a lot of flights, there were a lot of ground studies conducted, and after several months, USGS, the United States Geological Survey, released a report analyzing the exact location of the fires, a map of debris in the area after the towers collapsed, and a lot of different reports were generated, but none of the reports could be generated at the same time as, or a few days after the event, this terrible event happened. So in the end, the data were not as useful as it could be expected, because there was no high performance computing infrastructure available at the moment to process the data in real time. What can we do today in order to address this situation? Okay, today we have very low power, very compact, specialized hardware devices like FPGAs or GPUs that I mentioned before, that are even possible to be mounted on board the imaging instrument. And it doesn't necessarily need to be a satellite. It can be an airborne platform or even a drone. Even an UAV has now the capacity to have low power GPU embedded on board, and with some algorithms and with some hyperspectral camera to do the monitoring of a critical event such as this one in real time. So that's where the new possibilities of hyperspectral imaging are opening. Now we have a consolidated base of algorithms that has been developed over the years. But the most important thing, in my opinion, is that now we have the capacity to put this kind of instruments on board any imaging platform and perform some kind of real-time analysis. Of course, that has implications because, as you know, one of the most important things we need to do with the data is to perform some kind of corrections, geometrically, also atmospheric removal, and there are some also other kinds of pre-processing steps that need to be conducted before running a mixing algorithm or a deep learning algorithm to interpret the data. So that's still a challenge, but you can still also put these radiometric and geometric correction algorithms on board the imaging instrument and try to achieve a full real-time processing chain at the same time as the data are collected. So that's one of the things that we are going to discuss in this tutorial. And in my opinion, this is really the most important future perspective of hyperspectral data analysis. And we have been talking for many years about that, but we have come to a point that with, for example, with low power GPUs, such as the ones you have in smartphones, or very low power and radiation tolerant FPGAs, we can have even these hardware devices operating from space, from satellite instruments. So it's a really exciting time for hyperspectral data analysis and also for remote sensing data processing in general, because now we see very close how to do this kind of analysis in real time, at the same time as the data are collected. We have a question about, can mercury, lead pollution in water bodies be detected using hyperspectral imagery? I'm not aware of specific applications, but of course, this is something you can do, because for hyperspectral data, it's quite easy to perform target detection. If you know exactly the spectral composition and the material that you are looking, in this case, this kind of pollution, you just have a way to attack the problem that is, okay, you have spectral libraries, and I'm sure there are samples of mercury in such libraries, and you can do a mapping of this kind of pollution by simply analyzing the spectra of your hyperspectral image and looking at the correspondence with the spectral library material that you have. So in general, any material, any substance that you are interested can be mapped, efficiently mapped with hyperspectral data, because you have, probably you will have a very similar spectral signature already collected in a library, and you can use that signature library to match the spectral signatures that you are collecting in your data. So it's not only possible, but I would say it's very, very feasible. It's not a difficult problem. This is the kind of problem that hyperspectral data normally addresses in a very efficient way. Okay, so of course the spatial resolution is also very important, and ideally we would like to have very fine spectral and very fine spatial resolution, but this is generally not possible. And I'm giving you an example again with the World Trade Center data. At the left, you can see a high spatial resolution version of the data, and at the right, you can see a hyperspectral false color composition. That means we are taking 3 of the bands of the hyperspectral data and putting them together to create a false color composition. You can see that the spatial resolution is much worse in the hyperspectral data, but in turn, you get a much better spectral resolution. So that's why there are many studies right now that are focusing on performing data fusion, how to extrapolate the spectral resolution that you have on the left to the good spatial resolution. Ideally, you want to have the good spatial resolution on the left and the good spectral resolution on the right. So, for example, through spectral unmixing, you can perform a kind of fusion. You can do a sub-pixel interpretation of the coarse pixels in the rightmost part of the image, and somehow match those pixels to the fine spatial resolution pixels on the left. So as we will see later, spectral unmixing is a very important task for hyperspectral data exploitation because it somehow allows us to fuse high spatial resolution data with low spectral resolution and hyperspectral data, which, as we know, has very high spectral resolution, but maybe not so fine spatial resolution. So we will be talking about this a bit later. In order for you to conduct analysis, and especially for those of you who never work with hyperspectral data, I'm going to provide some places where you can obtain hyperspectral data cubes for free. The most popular one is the AMERSIE website, where you have this link. You can download free data from the AMERSIE data archive. Of course, one important thing is here you are going to collect full flight lines. So if we want to process these full flight lines, maybe you are dealing with gigabytes of data. So it's not the same to process a rather small, let's say, Indian Pines version of a hyperspectral data set that we are very used in our communities. Very small data is about 100 plus pixels, not more than 200 times 200. That's a very small data set. But a full flight line can be thousands of pixels by thousands of pixels in terms of spatial resolution. So in order to do this real hyperspectral data analysis, you need to perform hyperspectral analysis on high performance computing architectures. So that's why I feel hyperspectral algorithms should also take into account how efficient is their parallelization, because in real cases, in practice, it's difficult to process this data in a normal computer, and you really need to resort to some kind of accelerator or some kind of specialized platform in order to do the processing. Okay, so I'm going to let you login password in order to download the radiance of Moffett field. I think if you go to the website, it's better to look at there is a kind of navigator similar to Google Earth, where you can see the full flight lines where the data, the images can be downloaded. I think those data are free, the ones in the flight lines that are appearing on top of Google Earth. Let me search online, and I'm going to take a look at this. In the meantime, while I look at this in another computer, I'm going to let this slide so that you can briefly take a look, or if you want, you can try these other sources of free hyperspectral data. So I would like to call attention particularly on the first one, is the GRSS website that we have prepared to perform data analysis and standardized evaluation. So this website, DASE, is the GRSS effort to provide free hyperspectral data sets together with training and testing. And then you have other places, other links that I have been collecting these days in order to perform, download or to collect hyperspectral data. So just give me a couple of minutes. I'm going to test the question. I'm going to see what Andrius Opsianas was commenting about the need to provide a login and password. I'm going to try in another computer to figure out what is exactly the situation. So in the meantime, I'm going to let you hear exploring this. I will come back in 2 minutes with an answer to that question. Okay, so I had the chance to take a look at the material, and yes, of course, I will provide these slides for all the participants. And what I'm going to do is I'm going to show you the data portal of AMERSIE, which is where you can download the data. So I'm going to stop sharing the screen for 1 minute, and I'm going to share a different one where you can see the data portal of AMERSIE, which is the place that is most efficient for downloading the hyperspectral data. Okay, so I stop sharing this one, and I'm going to share this other one. I think you can see the address. So here is the AMERSIE data portal. You can see basically you can move all over the world to see where flight lines have been collected. Unfortunately, very few in Europe because most of the hyperspectral data campaigns have been performed in US. As you can see, there are many flight lines all over US, and also some in South America. Not really. Okay, I thought there were some campaigns in South America. So it's basically most of the data collections have been conducted in the north of America. So now you see the flight lines, and if you are interested in some of the flight lines, for example, we collected some data in the Gulf of Mexico because there was an oil spill there. You can see you can zoom, of course, and then you can see the description of the data, dimensions, number of data, and the quick look. You can see the RGB quick look. It will show you basically an overview of the data. For example, here you can see it has a lot of clouds. So this is a false color representation or even a grayscale representation with a lot of clouds. But the important part here is there was an oil spill in the Gulf of Mexico, so you can use the data for that kind of analysis. Let's move to another area. For instance, there's a very popular data set in California for agricultural studies, and it's near the area of San Francisco that has been very widely imaged. As you see, a lot of flight lines. So for instance, this is a data set collected over Central California, just west of Lake Tahoe, just east of Clear Lake. You can download the data in gradients units. You can download also the reflectance data, which is interesting because one is atmospherically corrected and the other is not. And of course, as in the previous case, you can see the quick look. So here you have an RGB representation of the data, which is huge, as you can see. You see the agricultural fields, and of course the data is completely geo-corrected. So there are lots of images available from the conducted by AMERSIE over the years. We can take a look, let's say now over an urban area. Let's go to the East Coast. Let me see if there are some hyperspectral data over Washington, D.C., for example, or New York. This is a famous data set, I believe, in Washington. So again, you can see the number of samples is 2,000, the number of lines is 4,000. This is much bigger than the usual sizes that we are processing in the hyperspectral community. And if we take a look at the RGB quick look, yeah, you see in this very high quality data with some different features, some kind of argon features. So you have plenty of data to process and analyze. The main problem is only a few data sets really comprise ground truth. So that's a challenge for the analysis. But okay, just in the JPL repository, you can download a lot of data and perform some data processing. I have a question from my good friend Roberto Camarero. He's talking about more and more computing power on board of the spacecraft. This is something you, Roberto, know well because you are an expert in this area. What would be for you the most useful use case for this onboard analysis approach? Oil spill, algae bloom, soil contamination. Well, there are many applications, and I would say I'm very interested in forest fires because in my region we have every year we have problems with forest fire, and there has been no way to really address this problem. But it's very difficult in the case of fires because we also need to look at winds and other parameters that are not only related with the image data. But yeah, the applications you mentioned, oil spill, soil contamination, are very important for onboard analysis. I think any environmental crisis or even the impact of an earthquake or a fire or kind of a typhoon, this kind of real-time applications that you need to monitor in a very quick and very fast way, like a flood, for example. This is where the hyperspectral technology can really provide a competitive difference with regards to other technologies because we have so many information that we can analyze in real time. Okay, so after taking a look at the data portal of JPL, I'm going to go back to the presentation, to the PowerPoint. So, of course, there are many other applications that are not related with remote sensing, and hyperspectral data are used also in fields like archaeology or medical imaging or even analyzing construction materials. There are many fields, but our focus on remote sensing leads me to discuss a little bit the type of remote sensing platforms that we can use to collect hyperspectral data. Of course, if we use a satellite, we have a wide and almost global coverage. For instance, you have the repository of Earth Observing 1, EO1 at USGS that I provided in the links in the previous slide with all the links for downloading hyperspectral data. And this is great because we can have a lot of information also from the temporal point of view. Because from the satellite, you normally have a revisit time. You can have the same area imaged every certain number of days. So you can perform multi-temporal analysis. Now, the option B is airborne instruments like flights, a la carte flights. This is the case of AMERSIE, as we saw before in the data portal. These are normally operated via projects or calls for opportunity to reserve a flight and to conduct a flight line over a certain area that has been of interest. For example, in the hyperspectral community, there's a mining district. It's called a Cuprite, which is near Nevada, near the city of Las Vegas, that has been imaged for 20 years. That's because the USGS, the United States Geological Survey, has conducted a lot of ground studies on minerals on that area. So eventually that site has been imaged very frequently with the airborne facility. So with an airborne facility, we can have temporal resolution, but it takes effort because we need to flight every year. And the coverage is also less wide, I would say, than satellites because the flights are more specific. We need to operate the plane to go to the same place, be lucky that there are no clouds, and collect the data. So that makes option C perhaps the most interesting these days because now drones are very cheap. They are an emerging platform with more control from our user point of view. We don't need to operate a flight, or we don't need a big organization. We can have our own drone. And right now we can have hyperspectral cameras and high performance computing devices on the drone. The main problem, the main issue here is the autonomy. How much time are we going to be able to fly the drone over a certain area? Because the autonomy time is not high, especially if you put a lot of hardware, if you put a lot of devices on board. And in this case, the energy consumption is a key issue. So we need onboard devices that can consume low power in order to have an option that is reasonable in terms of UAVs or drones. If you look at the hyperspectral instruments available today, and I'm only talking about airborne and satellite because drone is much wide diversity. Almost any group, every group can have his own drone and operate it in a way that is more commodity based. But you can see we are quite healthy in terms of hyperspectral instruments. We have the new generation of AMERSIE. We have initiatives from, for example, the Italian Space Agency, the German Space Agency. We have had Hyperion. We have from the Israel Space Agency. And I didn't list here, but in China, there are also many instruments, both on the satellite and airborne point of view. And if you look at the characteristics in terms of bands, spectral range, and spectral resolution, we have very sophisticated devices. For example, if we look at AMERSIE's new generation, there are 600 spectral bands in the range from 0.4 approximately to 2.5 microns. And the spectral resolution is only 5 nanometer. That means every band is only 5 nanometer away from the next band in the electromagnetic spectrum, which is almost contiguous. And the ground sampling distance, meaning the meters per pixel, is quite small, 0.3 to 4.0. That means we have high spatial resolution as compared to the previous version of AMERSIE that was 20 meter pixels. So every day we have more sophisticated instruments from the viewpoint of spectral and spatial resolution, and we even have more possibility for revisit time if you look at the satellite instruments. So it's really an exciting time for hyperspectral, because in Earth observation, it really came a point where we can have high spectral, spatial, and temporal resolution. But we need this kind of high performance computing architectures in order to process the vast amount of data that these instruments are generating. Which applications are particularly important? This is in relation to the question by Roberto, and I summarize here some of the areas in which high performance has been used in combination with hyperspectral data. For example, wildland fires in Spain and Portugal have been a very important issue for our group, and we have conducted many studies. But there are, for example, applications in biomass burning, like estimating subpixel temperatures and extent, smoke, combustion products, environmental hazards, like detection of contaminants, geological substrate, coastal and inland waters. In this case, the idea would be to identify chemical and biological stand of detection, like monitoring oil spills and so on. In ecology, we have applications related with chlorophyll, leaf water, lignin, cellulose, pigments, structure, other kind of constituents. There are, of course, commercial applications related with mineral exploration, agriculture, and forest status. And there is a wider range of military applications for which sometimes we don't have a lot of information because these are classified. These are related with detection of targets like landmines, decoys, concealed warfare, and so on. So I would say an important source of development in hyperspectral imaging is also the military applications. There are many projects and there are many applications related with military. And of course, high performance computing is also crucial in that area of analysis. Let's go back to the case study that I mentioned before, the September 11th World Trade Center hyperspectral data set. I'm talking about this because it became kind of a benchmark in particularly for high performance computing. And there are many things that we can do with the data, but another crucial thing is how to do these things in real time. So one thing we can do is to estimate fire temperatures, as you can see here, by looking at the slope of the spectral signature, and also even at saturation at certain parts of the spectrum, we can estimate the temperature of the hotspots in the field. By taking advantage of the detailed spectral information contained in the hyperspectral data, we can also produce maps with the fire temperature, asbestos, contamination, and debris spread. So this was done by USGS at the time of data collection. It could not be done in real time, but the maps were produced and they are available online for us to validate algorithms or to analyze how fast we can produce these products and see if we can produce them in the same time that the airborne instrument would be collecting the data. So in this particular case, for this image, for this subset that we will be analyzing later, it is estimated that AMERSIE takes about 5 seconds to collect this image dataset. This is a 140 megabyte image dataset. So there is a kind of challenge is how to produce these estimations of fire temperature or debris composition maps in 5 seconds for this image dataset, using, of course, all the bands. So this would be a good challenge to see if our technique is really working in real time. And also another important application related with this image is the detection of this contaminant material, this asbestos, which can be identified by their spectral signature. So this is also a challenge related with this data set. And an important thing is we have very detailed ground truth reference information, because for certain parts of the image, we have, for example, reference information available from USGS. Here you can see the spatial location of the thermal hotspots in the World Trade Center. So this means the fires that were still ongoing under the debris that were in the area. That means it was very difficult for people to see the fires with if we use, for example, optical image in color, we would not see these fires because they are hidden under the debris. But if we use a thermal band of the hyperspectral data, the fires can be seen very clearly because of the temperature. The temperature is so different from the surrounding. So one important source of reference information that allows us to validate algorithms is the location of the thermal hotspots in the World Trade Center area. And in this image, you can see the location of these fires in the image. So another challenge, another benchmark is, are we able to detect all these fires by doing some target detection or fire detection algorithm, and also do it in real time? So you can see how this image has been used very widely for not only information extraction purposes, but also to analyze how fast we can go with such information extraction. And here you have another map produced by USGS. This information is actually available at the USGS website, with not only the location of the fires, but also an estimation of the temperature of the fires. That can also be achieved by looking at the spectral signatures of the hyperspectral data. As mentioned before, by looking at the slope of the spectral signature and the saturation of the spectra in certain parts of the electromagnetic spectrum, we can estimate the temperature and even the coverage of the fire in the pixel. So this ground truth information will be used later on to analyze or to substantiate the performance of different algorithms that we are going to discuss. Okay, so we finished the first part, and now we are going to move on to an introduction to parallel processing. This is quite basic because I'm not sure if most of you have already been related to parallel processing, but I thought it would be good to give some general introduction about what means to process parallel tasks. So basically, software has been written for serial computation. Normally, every kind of software, or the majority of software that we use, has been designed to run on a single computer with a single central processing unit. However, in this case, we have a limitation. We have only one CPU and we have many instructions in which the problem is broken. So the instructions have to be executed one after another. That means only one instruction can be executed at any moment in time. In parallel computing or in parallel processing, the idea is that we have multiple compute resources. It can be multiple CPUs, or it can be a hardware accelerator, or it can be a cluster, it can be a multi-core processor, an heterogeneous system. But the fact is we have multiple CPUs. So the idea is to partition the problem in a different way so that each part is broken down to instructions that can be executed simultaneously. And the good thing is to have instructions that are not dependent on one another, because if we start having dependencies, we need to schedule the execution of instructions in different CPUs in a way that is arranged a priori. While if we have totally independent instructions, we can go ahead and just use a greedy approach in which we try to feed as many instructions as possible to each CPU. The reason for solving the problems in this way is that the real world is massively parallel. Parallel processing everywhere, in galaxies, planetary movement, even in rush hour traffic, automobile assembly lines, everything works in parallel. So why our programs, our software should run in serial way if we can take advantage of multiple processing units? There have been many applications of parallel processing historically to solve problems in atmosphere, Earth, environment, physics, bioscience, biotechnology, genetics, chemistry, molecular science. It is not new to remote sensing. It's also applied in many other areas, many other fields. Actually, with the modern computers, we always have a GPU accelerator. We always have some kind of multi-core processing environment. So the idea is not to limit ourselves to software that can be run only exploiting one CPU, but to develop software that can take advantage of multiple processing units. Some of the frameworks that we are using these days are already doing that automatically. For example, if you are programming in TensorFlow or Keras for deep learning, these frameworks already use the GPU in a way that is effective to run all the computations. So even if we are not specifically planning to use parallel processing, most of the frameworks or programming languages are de facto exploiting some kind of parallelism in the way they design codes and in the way they run our algorithms. So what are the reasons for using parallel processing? There are many important reasons. One is to save time or money, because in many cases, doing something in parallel will short the time to completion of the task, and this has potential cost saving. And also the reason that parallel computers are now very cheap. If you look at the top 500 list of the fastest supercomputers in the world, you can see that most of the fastest computer devices are now clusters of GPUs. The reason is simple. A cluster is cheap and a GPU is cheap. So putting them together is a very cheap way to build a very fast supercomputer. These supercomputers allow us to solve larger problems that are difficult to solve in a single computer and provide concurrency. That means that we can do many things at the same time, so we can solve the problem in a more effective way. And an additional advantage is we have the possibility to use non-local resources. That means we don't really need the computers to be located in the same place, but also we can have computers that are located in different places around the world. So we have a kind of distributed processing to perform massively parallel computation using different geographic locations. So if we look at who is doing parallel processing around the world, we can also conclude that parallel processing is a good business. Not only people in academia are using parallel processing, but also, as you can see, there are many industrial partners that are exploiting parallel computers and supercomputers. That means if the companies are involved, there is something about the business here. And there's also a significant percentage of classified partners, probably in military, that are also exploiting parallel processing, but are not really releasing the use of these parallel supercomputers. Regarding the topics, geophysics and remote sensing constitute a very important application domain for parallel processing. And it's interesting to see that there are some fields that still can be developed, for example, medical imaging or other fields that one would expect to be more involved, like aerospace or even gaming, although gaming is now taking advantage of online game services for, exploiting GPUs for video consoles, PlayStation, Xbox, and so on. But I really feel there is still some development, some possibilities for development of parallel processing in the different areas of science and academia. One important thing when we talk about parallel processing is load balance, because normally when we have a parallel processing or a parallel problem that we want to solve, the computing resources are going to be heterogeneous. That means normally we don't have the same kind of processor in the cluster. Maybe the cluster is made up of different kind of CPUs, compute nodes with different memory, different communication networks. So in the end, load balancing is one of the basic first things that we need to do when we apply parallel processing, because we need to distribute the tasks in a way that all the compute nodes more or less accomplish the same tasks in the same amount of time. So if we give a lot of workload to a computer that is very slow, it is likely that this computer is going to delay other computers that will finish early. So it's quite important to reduce these orange times here in the slide, which are the waiting times, and make sure that all tasks are more or less the same in terms of working time. So this is something that requires a knowledge about the architecture that we need to have in advance in order to be able to distribute the tasks in a way that is efficient and balanced. Another important aspect of parallel processing is communication, because as you know, or you can probably imagine, the communication network is perhaps the most important bottleneck when we are distributing tasks among computers. And this is particularly important if we have computers distributed in different geographic locations around the world. So there are different kinds of communications, and I try to summarize all of them in the slide. So we have point-to-point. In this case, one of the nodes is acting as the sender, and another one single node is acting as the receiver. And then we have collective communication, which are the most complex and potentially harmful for parallel efficiency, because they involve sharing data between more than two tasks. We are not point-to-point anymore. And this can be specified as being members in a common group or collective. There are some variations, like the broadcast, in which one piece of data is distributed as it is without modification to a set of distributed processing nodes. We have the scatter, in which the chunk of data is partitioned and only separated pieces are provided to different nodes. The gather is the opposite operation, in which different computers are providing pieces of data that are combined in a single location, probably after doing some independent calculation with the local parts. And then the reduction is an operation in which arithmetically we can combine, for example, a set of numbers into a single number by means of a sum or a different arithmetic operation. So these are 4 examples of collective communications that we face normally in parallel and distributed applications. Okay, so after this introduction to parallel processing, we are going to discuss data partitioning strategies. As we saw in the previous slide, normally we have scatter and gather. The idea is to partition the data and distribute it so that different nodes can perform different computations with isolated parts, distinctive parts of the original data, which could be a hyperspectral image. So how this applies to hyperspectral imaging? There are two kinds of partitioning that we can apply for remote sensing data. One possibility is to perform spectral domain partitioning. That means that a single spectral signature, a single pixel vector, may be stored in different processing units. And in this case, I don't think it's a very good idea to do this kind of partitioning because each pixel would require communications. Remember, in the past, we have identified the spectral signature, the full spectral signature, as the minimum unit of computation for most hyperspectral imaging applications, like a mixing, classification, and so on. So if we partition each spectral signature into different computing nodes, we are going to have a lot of communication. It's much better to keep full spectral signatures at the same compute node whenever possible in order to avoid these communications, because in the end, communications can saturate the system and lead to bad performance in terms of parallel computing. So in general, in hyperspectral imaging, we are going to go for this kind of spatial domain partitioning in which every pixel vector is normally stored in the same processing unit, which is beneficial, for example, for sliding window approaches in terms of low-level image processing and spatial spectral data integration. This is an example of an embarrassingly data parallel partitioning. We have the original hyperspectral image. We have two partitions in the spatial domain. That means we are not partitioning the spectral signatures. We are keeping them in the same compute node. We have two nodes in this simple example. So we are scattering the hyperspectral image in two parts. We are computing some local results, and we are gathering everything into a final result. So this is an example of a collective communication of scatter and gather using hyperspectral data. As you can see here, the amount of interprocessor communications is very small because we could partition the data and we don't need to communicate anything between processing node 1 and processing node 2. So each working node should receive a partition that is proportional to its characteristics in terms of speed, and also we should also take into account the communication network. So this is an example of easy or embarrassingly parallel data partition. One evolution of this kind of approach is the master-slave dynamic work assignment, in which we have a master processor and 4 slaves. And the idea is the master distributes the working load among the slaves so that the slaves perform some local computation, and then maybe some of the slaves return some results to the master node. So this is the best scenario that we can have in parallel processing, a problem in which a master node can distribute this working load to the different processors. So is this how Google Earth Engine works, spatial partitioning? Depends on the algorithm, but in most cases, this is the way it does, because as you know, Costas, there is a possibility to add a layer of computation on top of Google Earth Engine. And in this case, yeah, when you, for example, zoom with Google Earth, you know, Google Earth is a mosaic of data collected from different satellites. So in the end, it's a composition. And if you're lucky and the computation that you need to perform is completely independent, for example, you want to process data of the whole Spain, you are not going to do it in one shot. You need to partition the data into different portions. And you also need to perform the computation in a way that is completely independent. So the most reasonable way for Google Earth to do it is to apply this kind of master-slave dynamic assignment. That means that we take advantage of the fact that Google is already running in a cluster. So we perform the computation and the processing of different chunks of the data in different parts of the cluster. So I would say this master-slave approach fits perfectly the architecture of of Google Earth because it's also based on a cluster. Of course, it would be very important to define the level of spatial resolution at which we want to do the processing, because as you know, Google Earth has different levels of spatial resolution. So one possibility is to perform the analysis at the highest spatial resolution available. In this case, we need more nodes to perform the computation because it's a more computationally demanding task. But if you have a lower spatial resolution, then eventually you could do the processing in one node. Imagine that you are going to process the whole map of Spain in a very low spatial resolution. Maybe you don't need to do it in parallel. Maybe you can run at this coarse spatial resolution level in a single CPU. But in general, the answer is yes. You can take advantage of this master-slave simple partitioning for processing large databases like Google Earth or other kind of remote sensing data archives. Okay, so of course this master-slave dynamic work assignment can have multiple iterations. We can now return some data and start again. Now, there are some algorithms for image processing that are based on windows, on moving windows, for example, for filtering or for doing some neighboring computation. There is a general way to include spatial information into the analysis by looking at spatial neighborhoods, or even the concept of superpixel, which is a kind of region in the data. And I just wanted to mention that because this kind of window-based or superpixel-based algorithms generally involve some problems in the analysis. There is a decision we need to make whether we want to communicate data or we want to replicate data. For example, in this case, we are just moving a sliding window over the pixels of the different partitions to perform some local computation and then obtain a final classification map. So somehow we are avoiding the communication between the two processing nodes. In this case, we can have some problems in the border of the image because we have, for example, a 3x3 window or structuring element in this case, because this is a morphological algorithm. You can see there are some pixels that eventually will fall outside the image domain. So in this case, normally the pixels that are not in the image domain are disregarded in the calculation of the morphological operation. So even if we have a 3x3 window here, since the target is this central pixel, we can use only the neighbors that are present in the image domain to perform the final computation, in this case, the morphological eccentricity index for that pixel. So that's not really a problem, how to deal with the image data that are not in the local partition. But we have a problem when we perform the computation on the boundary of the data. Morphological operations are a kind of spatial operations that are related to how a pixel behaves with regards to the neighbors, how similar a pixel is with regards to the surrounding pixels in the image scene. So there is a theory, mathematical morphology theory, that introduced several kind of filters and properties in order to understand how homogeneous a pixel is with regards to the neighboring ones. That's why we have these windows, normally fixed window sizes, in order to understand, for example, what is the gray level of this pixel in comparison with the neighbors. In hyperspectral data, of course, we extend the concept to how the spectral signature of this pixel is with regards to the other surrounding pixels. And it gives an idea of, for example, whether an area is homogeneous, or we have some image borders, or we have some object in the area. So it's a way basically to include the spatial information in the spectral analysis of hyperspectral data, because we mentioned that not only the spectral information is important, but also the spatial information. So we deal with this kind of kernels, and what I wanted to emphasize is what happens here if we have a kernel that is that needs to be processed for the neighbors of a given pixel, but some of the neighbors are no longer in the local partition because we have partitioned the data and sent to a different processor. Here we have a problem because we need to send some boundary data from one processor to another in order to be able to complete the computation, the morphological computation for this pixel. We need to analyze these pixels that are close, especially to this one that we are analyzing, but are actually located in a different processor after the partitioning. So we have two ways to handle this problem. One is to send this pixel data, these pixel vectors from one processor to the local processor. But eventually this is a lot of information because remember, each pixel vector is high dimensional. We have a lot of values for the pixel vector. So communicating this information for all the windows and for all the pixels will introduce a lot of redundancy and a lot of communications over the system. So one thing that parallel programmers have done in order to solve this problem is to introduce an overlapping scatter. An overlapping scatter means that instead of communicating this pixel data, this pixel row of vectors that we need to complete this calculation, we simply assume that this row is replicated in the two processors. So we are having a somehow non-disjoint partitioning of the data. We have some redundant computation to be performed, some redundant data in the two partitions. That means we are going to have some repeated information, because the ideal situation is to have no redundancy at all. But eventually this redundancy can help in the parallel processing because we can avoid communicating the data since we have replicated the data here. Of course, this works for small kernels. If we have a 3x3 kernel, we only need to replicate one row of information because with this, we basically solve the problem. But imagine that we have a bigger kernel, like a 5x5 or 7x7. We would need to copy or to replicate more rows from one partition to the other, and the amount of non-disjoint information would increase. So in this case, there is a balance between how much redundant information we include in the system and how much communications we are willing to assume. So just to give you an idea of how these different strategies work, I have here an implementation. I'm showing you some results in a cluster. Thunderhead is a NASA cluster with 256 processors. And what I'm showing you is the implementation of a simple morphological operation with the windows based on redundant computations and inter-processors communications. So we have one iteration means we do 3x3 kernel, 3 iterations means we do 7x7 kernel, and 5 iterations means we do bigger kernel, in this case 15x15. So what we are doing here is to compare the impact of including redundant computations versus communicating all the information that we have in the system. So it's again the idea of using an overlapping scatter versus communicating the data through the communication network of the system. And as you can see, the metric that we are using to evaluate is the speed up. The speed up is how many times we go faster as we use more processing units in the cluster. So ideally, if we use 256 CPUs, we would go 256 times faster. This would be linear speed up, perfect speed up. However, you can see with redundant computations, we cannot get perfect speed up, but we get quite close to perfect speed up. We get actually the redundant computation time and interpretation communication time in seconds can be seen in this plot, and we get a speed up that is about 200 in the best case. In the case with more iterations, so basically redundant computations can benefit from since we have a lot of computation, we can get a better speed up in the case of more iterations. However, if you look at the plot of interprocessor communications, you can see how the speed ups degrade with the number of processing units, and at some point become almost stable, almost the same time. We don't get a significant increase, and we are getting far away from the linear speed up that is the optimal result in this particular case. You will see later that there are even cases in which the speed up can go down significantly after a certain number of nodes. That means that the impact of including additional nodes is no longer helping the problem. So this example gives you an idea of what is the impact of using redundant computation versus communications. Okay, so we are going to quickly address this section, and then we will have a coffee break to relax a little bit. So I'm going to talk a little bit about parallel processing on clusters and heterogeneous networks, and then if you agree, we will have a coffee break. So these issues that we are discussing about the speed up, of course, depend on the kind of parallel computing platform that we are using. The speed up is formally defined as the performance that we obtain using a number of processors, in this case P processors, versus one processor. So you can think of many different kinds of clusters, like a mini cluster or a Earth simulator, which has a very high number of processors. In all cases, the most difficult thing for a cluster is the maintenance, how to maintain, how to for example, in this system over here, it needs a lot of energy, it needs air conditioning system, every processor can have a failure. The maintenance is very, very difficult. If we have an optimal scenario, the speed up would be linear. This is what we mentioned before. We increase the number of times we go faster linearly with the number of processors, but also we can have speed up problems, in the sense that the more the processors, we can have a flattening of the speed up curve, like in this figure on the left, or even we can have the worst possible performance, the worst possible scenario in parallel algorithms, that is, with more processors, we even reduce the speed up. That means that at some point, it starts to be more efficient, more feasible to do serial processing rather than parallel processing. So we need to avoid this situation. Let's go back to Thunderhead, which is a NASA cluster that I mentioned before, and it has a total of 256 processors. And I'm showing you some different implementations of algorithms for, remember, unmixing, spectral unmixing. There are pure spectral signatures that we need to identify in the data. So in this comparison, I'm just showing you the properties of different algorithms for looking for the end members in the hyperspectral data. So this would be part of an unmixing application. And you can see that we can go from very high processing times in terms of seconds to almost real-time performance using 256 processors. We have been discussing that the World Trade Center data set needs 5 seconds to be collected on board. So as you can see in a cluster, at least one of the steps of the processing, which is end member extraction by means of 4 different algorithms, can be achieved in near real time. We can detect the end members in almost 5 seconds, a little bit more. But the main problem here is that a cluster cannot be used for onboard real-time processing, because a cluster is very heavy, it needs to be maintained, it needs to be operated. There is no going to put a cluster into even an airborne platform. It's too heavy and it requires too much power consumption. So a critical thing is how to do this with a system or a high-performance computer that can offer the same performance, the same computational power, and much less weight and energy consumption. Now, one possibility is to try a smaller heterogeneous system, like a network of, say, 10 or 16 processors. But in this case, even the partitioning of hyperspectral data becomes very complicated, because normally these heterogeneous networks are based on computing resources that are not the same. They have different processing power, and even the communication power, the communication of the network has different properties. So I'm showing you here an example of a code that we developed to partition a hyperspectral data set into 16 heterogeneous partitions, you can see that the size of the partitions is different because the network of processors are different in terms of speed. And basically, the communication happens in a way that we work in columns. So for the leftmost column, we send the overlap borders to processor in the first column and wait for the other lap of processors in that column. In general, this is very difficult to implement. The implementation is not easy because we first need to estimate the processing power of the computers, and then we need to estimate the velocity of the communication network. I will show you later the results for this implementation, but we have some problems in terms of how to effectively develop the code. So in the next section, we are going to analyze how to perform parallel processing in specialized hardware devices. And we are going to talk mainly about FPGAs and GPUs, which is the real solution for computational processing on board the hyperspectral imaging instrument. So I'm going to continue with the parallel processing in specialized hardware. And this is quite a relevant part of the tutorial because it comprises most of the more advanced developments in the field. So why onboard processing? The first reason why we are thinking about conducting onboard processing for so many years is the real-time requirements in many applications that have large data volume, large cost and complexity, and we need to have a critical decision latency. That means we need to provide a response in applications in which we need to perform very fast analysis of the data. So automatic onboard processing can reduce the cost and the complexity of the ground segment of the mission, and also enable autonomous decision to be taken on board, while at the same time reduce the communication bandwidth. And the applications are many. I think we already discussed about time-critical applications, military applications, even for planetary exploration, we need to perform onboard processing at the same time as the data are collected. I can see there is a question. What could be a possible thought process for implementing a new custom algorithm to be implemented parallelly? I think this is a very important question because sometimes when we develop algorithms for hyperspectral data analysis, we never think about how these algorithms can be efficiently implemented in parallel. So in my opinion, in the future, the most important algorithms are or will be those that can be efficiently parallelized, because sometimes we have very sophisticated, like neural network based or complex classifiers that eventually do not map well into hardware. So the trade-off between the classification accuracy or the performance accuracy of the algorithm and the simplicity for parallel implementation will be a very important parameter, in my opinion. I think in current days, we have a suite of algorithms that is very wide. We have many different techniques. We have classification accuracies that are very high for most hyperspectral imaging datasets. But we really need to conduct an assessment of which algorithms can be simply performed in hardware, because these algorithms will have a lot of chance to survive or to be used more often than other algorithms, in my opinion. And then you mentioned about the results of processing on the WTC data and the time it took for processing. Does the processing speed up bring any trade-off with accuracy evaluation results? Yes, we will talk about this later, because of course, in this time-critical application, the most important thing is to have a result in real time. So we don't care only about the accuracy of the result. We can sacrifice a little bit of accuracy in favor of meeting the time constraints of the application. So later on in the tutorial, I will talk about this, and I have an example describing the trade-off between computational performance and accuracy in the World Trade Center application. So we will see later about that in the tutorial. So going on with the onboard processing, one of the solutions has been reconfigurable computing. That's basically FPGAs. The problems we have as mentioned, are related with high computational complexity. Different algorithms need to perform different imaging applications, like, for example, classification, target detection, and mixing. Even compression is very important to do compression on board to optimize the downlink or the sending of the data from the satellite to the ground station. So it's very appealing to have the possibility to dynamically reconfigurable the hardware that we have on the sensor. So reconfigurable computing provides a reality, it's no longer a promise. We can have an FPGA with several algorithms implemented on the same board and be able to dynamically select one out of a pool of algorithms from a control station. So in general, reconfigurable computing is a very appealing solution, but recently a discussion has been put in place in the community, because normally in order to develop algorithms for FPGAs, we need to overcome some difficulties in the programming that are not so serious when you use other platforms like GPUs, for example, like graphic processing units that are very simple to program in comparison to field programmable gate arrays. So now, even though FPGAs are currently the tool of choice for onboard computing, we can see more and more projects, as I will discuss later, which are based on GPUs of low power consumption, because in general, GPUs consume much more than FPGAs, in order to implement onboard missions for hyperspectral data exploitation. So in general, why reconfigurable computing is a very good solution for onboard compression or processing. We have increased requirement for downlink bandwidth limits in hyperspectral imaging sensors that are producing data at very high rates. So not only the analysis, but also the compression of hyperspectral data on board provides some benefits, such as to be able to develop scalable and adaptable architectures for multiple missions, and also to develop tools and software to support the deployment of applications on such a system. Some problems need to be overcome, not only for reconfigurable computing, but also for GPU computing. One is the radiation hard design considerations. These pieces of hardware are not made to be operated on space. So for example, if you put an FPGA or a GPU in a satellite platform, there are going to be problems of hardware degradation, failures in the hardware, power consumption issues. Of course, the hardware cannot consume a lot. If you think about a satellite mission, the power consumption is very restricted. And also, this is a new technology, especially there is a learning curve in reconfigurable computing in FPGAs, because this is not easy, it's not really easy to develop new algorithms for FPGAs. So we have a high potential for risk and need of proof of concept systems and algorithms. But you know, there are many advantages in the sense that there are many algorithms that have been now implemented in FPGAs, and we can also adapt algorithms from other areas like multimedia and video processing. So in this slide, you can see an example of a piece of hardware for onboard data compression. As you see, there are many nodes, many modules here related with the electronics of the system, the spectrometers, the optics, the calibration, and so on. But the only thing you need to do in order to perform data compression is to add a module on board that is based on FPGAs, in this particular case, that performs the compression after the onboard calibration of the instrument and the data. So it's not so complicated to add a new module for data processing or compression and integrate it into a system that is already operating. Of course, it needs to be certified for space operation, which can take time. And that means if you develop an algorithm for FPGA, let's say, that FPGA should be certified for space operation. But right now the process is getting faster, and I believe it's a very good option to use reconfigurable computing for onboard data processing and compression. I can see a couple of questions. What courses one should go through to learn spectral and mixing? I will talk about this later because I have a case study about spectral and mixing. And what are few platform frameworks to test various unmixing algorithms at once? Is your Hypermix tool going to be updated for newer algorithms? Well, the development of Hypermix has been kind of, not going steadily through time, because it's based on who is available or who in my group is available to include new unmixing algorithms. But we have planned to include some new algorithms in Hypermix, particularly those that are implemented in GPUs. I will discuss also about this later when I talk about unmixing, which will be in about 15 minutes when we go to the case study. So for the questions of Chirag, I think we can discuss a little bit about this later, or even offline after the tutorial. I can provide an update. Adriano is asking, how many compression losses are you willing to accept? For example, how it degrades the classification performance. This is really a very good question, and it depends on the application at hand. I would say lossy compression is always the choice, because lossless is really difficult to perform, not only in terms of onboard, but also in terms of the compression ratio that we can achieve, which is not more than 3:1 compression in the case of lossless. So about lossy compression, it's really a trade-off of the application, but I don't have information about this in the course, but it depends on the application. For example, we have seen that for a mixing, it's really critical to have a not so big compression ratio, because that degrades the quality of the end members, and then the mixing suffers a lot from a high compression ratio. But interestingly enough, for classification, sometimes a high compression ratio even benefits the classification, because high compression means you smooth things, you make things more homogeneous. It's like you are applying a kind of spatial filter, which is something that we do naturally before spectral classification. We do some kind of spatial smoothing or spatial integration. And interestingly, we have a paper that discusses different compression ratios, lossy compression in terms of classification performance. And sometimes high compression can benefit classification, but it degrades severely the spectral mixing. So that's why it's really dependent on the application domain. Hope this answers the question. Okay, so in the world of integrated circuits, we have many kind of circuits, but we are going to focus on the ones that are user programmable to describe FPGAs, which sometimes are based on the incorporation of lookup tables. It's a mechanism to simplify the implementation of parallel algorithms. So what is the difference between traditional ASIC circuits and FPGAs? For ASIC, the design has to be done in advance. It has to be defined to the company or to the vendor for the design of the circuit. So it's designed all the way in advance, from a behavioral description to physical layout. Now in FPGA, the things are completely different, because the FPGA is completely adaptable. There is no physical layout in advance, but instead we can reconfigure the device as we exploit the data or as we operate it. So it's really an off-the-shelf development that can be reconfigured by designers themselves. What is an FPGA? So as you can see in the slide, the FPGA is a very simple hardware architecture. It's a matrix of blank cells called configurable logic blocks, CLBs. And this device has the property that every cell in the matrix can behave as an AND gate, an OR gate, or a simple multiplexer. So that allows us to implement any digital circuit, provided that we have a sufficient number of logic blocks. One of the most popular architectures for onboard exploitation has been the Vertex architecture of Xilinx. I'm here describing Xilinx Vertex 2. And the main advantage of FPGAs is that their content is completely dynamic and reconfigurable. We can have different algorithms implemented in the same board, and we can change them as often as desired without having to remove the FPGA chip and replace it with a new one. So imagine the advantages. We have an FPGA on board a satellite or a nano satellite or a UAV, whatever platform you want to have. If you want to modify the type of algorithm that you want to apply in a given scenario, let's say you want to do compression, but then you want to do classification, then you want to do a mixing, you can change this without the need to install new hardware on the sensor. You can simply, from the ground control station, modify or reconfigure the hardware so that a different technique will be applied on board. Of course, this requires some additional logic. Just the reconfigurability of the hardware requires logic, a high percentage of logic to be used. But it's really interesting because even though we are not making full use of the hardware, we could technically include a new algorithm that has been developed very recently from the ground station without changing anything in the satellite. So that's really a very good solution for any kind of exploitation and operation, not even a mixing or a classification or compression. I can see Roberto Camarero, who is an expert in the field, recommends lossless and near lossless CCSDS compressor from Hyperspectral Data. And he points out that in the lossy mode, the user can define the maximum allowed error in the data. So as Roberto pointed out, even for compression, we can run different frameworks, and these frameworks have different tolerance parameters. So we can decide how much quality we want to sacrifice and what is the cost performance ratio, in a sense, between the outcome we are going to obtain and the property that we are embedding in the hardware. So this is a really interesting development. Now, the main concern, the main criticism I have, and this is a personal thing, with FPGAs is that the design is quite difficult. I'm not an expert in VHDL. I know there might be people who would disagree with this statement, but whenever in our group try to implement something in FPGAs, it was a pain. It was very difficult because FPGA design is a complex procedure involving very different steps, different software environments. The synthesis of the circuit can take a significant amount of time. And once the design has been synthesized, you normally need to conduct corrections and to refine the implementation. I'm aware that there are automatic tools right now that allow you to perform the codification in high level. But still, I find some problem from that viewpoint, in the sense that, at least for me and the people in my group, it's normally a very time-consuming process to perform an implementation of any algorithm, a mixing, classification, compression, whatever, in an FPGA. Maybe this is because we are not experts in the field. So once the FPGA has been synthesized and simulated, it is ready for implementation. The synthesis can take a significant amount of time. And also the reconfigurability is also consuming a lot of logic resources in the chip. So you end up with a much smaller amount of logic that you initially thought you had. So these problems are there, and I believe it's fair to mention, even though FPGA has been very successful and it's currently the tool of choice for onboard processing. It's difficult from the viewpoint of implementation. The simulation and the validation of the circuit and the testing takes time. And then finally, the reconfigurability also takes a lot of resources on the platform that reduce the possibility to have too many algorithms implemented at the same time. The Xilinx has been very successful in developing architectures that have been certified. For example, Vertex 2 is a classic example of a certified architecture for onboard satellite operation. And we have some results that I will show later about the implementation of mixing algorithms in this chip and also in the Vertex 4 and other new families. Even the Space Cube, which is a radiation hard development at NASA, was based on Virtex 4 commercial family of FPGAs in the second version. And now, just to give you an idea, the third generation Space Cube 3.0 has switched from FPGAs to GPUs. So now it's based on NVIDIA Jetson GPUs, that is very low power consumption in comparison to FPGAs. This represents a significant evolution in the field because it means NASA is now looking at GPUs instead of FPGAs for developing space cubes or nanosatellites, in this case for hyperspectral technology. So I believe this is quite significant, and it might be related with the complexity of developing algorithms in FPGAs, and also related as well to the logic, to the amount of logic that it requires to have several algorithms implemented on board. This Space Cube is meant to be used in CubeSats, although it's still under development. It has not been tested operationally yet. It has not been sent to space, the 3.0 version. But yeah, the idea is to have a kind of CubeSat with processing power that is based on a low power GPU, which is a significant development in the field based on the recent literature that was always based on FPGAs. So now let's talk a little bit about GPUs. What are the advantages and disadvantages of GPUs, not only versus clusters, but also versus FPGAs and other platforms for onboard computation? So in terms of operation and management, a GPU is much easier to manage than a cluster, of course. It's compact, it's fast, it's quite cheap, and it can provide the same or similar peak performance than a large cluster. Of course, if we use the right algorithm. There are some algorithms that are not well suited for GPUs because of the architectures. We need parallel tasks that are independent. And in general, GPUs are quite appealing in terms of power consumption, performance, and cost. But we need to find the right algorithm to exploit a GPU. Now, as I mentioned before, if we look at the top 500 list of supercomputers, it's a very easy way to create a fast and cheap supercomputer. You have a cluster with a general cost of about, let's say, 10,000 euros. The GPUs are so cheap. For example, you could use Tesla architecture that is quite old, but very, very cheap these days. It's almost no cost to include the same number of GPUs as nodes you have in a cluster. And by the increase of the number of nodes, you can have, for the same price, a cluster of GPUs that will provide you a very significant increase in peak performance. Now, the ability to do GPU, which is general purpose graphics processing units, has boosted somehow the use of GPUs in many different applications, not only in remote sensing, but also in image processing, computational geoscience, and so on. And particularly the potential of GPUs for onboard processing comes from the fact that we have a new architecture that is very easy to program and is massively parallel in the sense that we have a lot of multiprocessors, each one with a lot of processing cores. So basically the architecture of the GPU is very well suited to parallel tasks that don't have a lot of interaction or a lot of communication. So in the future, as Roberto is discussing, there can be some advantages of using GPUs instead of FPGAs. And as mentioned in the comment, GPU is right now at this time making its way into space. So Roberto provided an interesting link to read more about that. I really feel we are in a time-changing moment in the sense that GPUs are really now being considered as a possibility for onboard processing. This possibility has been pointed for many years, but is coming to reality right now at this moment. This is partly due to the programmability of GPUs. In the past, all the programming languages for GPUs were very low level, very close to assembly. Of course, the explosion of GPU came with CUDA, NVIDIA CUDA. NVIDIA is the main vendor of GPUs all over the world. And they developed a language that is specifically tailored to their NVIDIA GPUs. But right now we have other solutions like OpenCL, even OpenACC, and other multi-core based solutions that allow us to program any kind of GPU, not only those from NVIDIA, but also from AMD and those for mobiles, low power ones, and so on. It is possible to run multiple replicas in a single GPU. Yes, this question is interesting because we can use a single GPU like a reconfigurable device, in the sense that we can have different kernels that we exploit as we desire. So in a single GPU, we can also have different algorithms implemented in advance, and we can run different kernels in the GPU, which is exactly the same property of the FPGA reconfigurability. So yes, with the GPU, we can also have reconfigurability by means of executing different kernels. So now that this programmability issue is solved, we have an architecture that is very appealing for parallel processing. As I mentioned, the GPU is particularly suited for embarrassingly parallel and repetitive computation. So we might have problems with algorithms that have some kind of communication, or even with recursive codes. They are not well suited to the CPU. But you can see how the organization of cores in the GPU is arranged. We have a set of multiprocessors that are basically groups of cores that share a common cache memory and a common logic, so a common control logic. So eventually we have a main memory. This DRAM memory is the same as the one in the CPU. This is a multi-core with 4 cores. And here we have a many-core, which is the GPU with many multiprocessors, each one having hundreds or a certain number of cores. It depends on the architecture, but generally the number of cores is ever increasing, as much as the power consumption allows, because the trade-off here is how to have more cores working simultaneously without consuming a lot of power. And the main memory in the GPU is the video memory. So it's kind of equivalent to the main memory of the multi-core. As you can see, the arrangement of the cache and the control in the multi-core is completely different. So the GPU architecture can be seen as an abstraction in which we have n multiprocessors available to the programmer. In each multiprocessor, you can see we have the cores, the processing cores, and we have different memory levels. We have the registers associated to the cores. We have some local memories like the constant cache, the texture cache, and particularly the shared cache memory. So if we are able to make the cores in each multiprocessor work only with data that are stored in the local memory, in the shared memory, we are going to have very fast processing, because the cores are very specialized. They are generally designed for matrix or vector operations. And also exploiting the local cache memories is very fast, because these memories are extremely fast compared to the global memory. Now, if our implementation is not good enough to make good use of the local cache memories, if we need to go to the global video memory, we need to pay somehow hundreds of cycles more in the processing, because the latency of this memory is much higher than the latency of the shared memories. So basically the design of GPU algorithms is a game about how to keep these shared memories and these cores in the local multiprocessors as busy as possible without the need to resort to other multiprocessors externally or to the global memory. So if the processes are conveniently allocated to the cores and the shared memory is properly exploited, we can have very high speed ups. However, if we have a lot of communication, or if we need to use the video memory, the global memory a lot, the computational performance is going to decrease. That's why programming a GPU has also some tricks. I would say not as many as FPGA, which in my opinion is more complicated. But the good thing is with CUDA, OpenCL, all these languages that we have today many of these tasks are automatically done by the compiler. So even if we define, let's say, a number of threads that is not suitable for the architecture, the compiler will correct that in real time and will optimize the code so that we have less accesses to global memory. So it's a very interesting development, because thanks to these high-level programming languages, we can have C code ported into GPU code in a very easy way. We have our C program. We just need to add a few kernels that are related to the parts of the code that can be implemented in parallel, and just run those kernels on the GPU while the rest of the part will run normally on the CPU. And that's really easy in terms of developing new algorithms, because we don't even need to care about how to separate the parallel part from the serial part of the code, as the compiler, the NVIDIA compiler or the OpenCL compiler will automatically do that. In the end, we end up with an executable file that can be executed in a heterogeneous system made up of a CPU and a GPU, and we can get much better performance than, for example, a multi-core, as shown in this example. Now, regarding how the threads, the computing threads, which are the independent units of computation, are distributed, we have a kind of arrangement in the GPU that is based on kernels. The kernel is the minimum unit of parallel computation that we are going to run in the GPU. Normally, a kernel is associated to a parallel function, a parallel code that we execute. Let's say a product of vectors in order to compute the spectral angle of two spectral signatures. That would be a kernel for hyperspectral image processing. So we need to decide how many threads we want to use to run that kernel, ideally as many as possible. So there is a high-level abstraction that is the block. The block is given by all the threads that share a common cache memory. So that is defined by the number of cores that we have in each multiprocessor. Ideally, we want to have as many threads as processors or cores we have in a multiprocessor. And then we have another level of abstraction, which is the grid. The grid is how many blocks of threads we need to perform the computation. As you can see in this figure, each GPU is a conjunction of multiple multiprocessors. We not only need to use one multiprocessor, but ideally we want to use as many multiprocessors as possible. In that way, we will have more cores and we will have more threads in parallel. So the level of abstraction is the grid. The grid is associated to the kernel, and the grid defines how many blocks we are going to have to solve the problem. In each block, we will have a number of threads that is given by the number of cores that we have in a given multiprocessor. That means that all the threads in a given block share one memory, the cache memory. And if we need to communicate one thread from one block to one thread in a different block, we need to go through the main memory, the device memory, that is the video memory, which is much slower than the shared memory. So we want to avoid as much as possible the communications outside the block, because that means we will not be using the local cache memory. Again, when you decide the kernel, when you design the kernel in CUDA, this is more or less managed compiler when you perform the compilation of the code. At that time, the number of threads and the arrangement of the threads will be automatically managed by the CUDA system, so as to make it as efficient as possible. So that's another advantage and a feature that I didn't see when I use FPGAs, which was more difficult in reality for implementation. Okay, so I'm going to show some typical architectures for GPU. This is the Tesla. You can see it's based on 8 multiprocessors, each with 16 cores for a total of 240 Steam processors. This one is approved for onboard exploitation. It has been certified, but it doesn't need to be a commercial GPU. For example, the PlayStation 5 will incorporate a latest generation GPU. It will be optimized for gaming, but it has high computational power, low energy consumption, and low cost because of the need to sell video game consoles. So probably this will be another interesting GPU for onboard exploitation, because it has been optimized even for a different field, but we can take advantage. And the most clear example is the GPUs that are now incorporated in smartphones, which are currently being analyzed as potential hardware components for onboard processing in satellite and nano-satellite missions. You can see the characteristics of these devices are much less than, so to say, professional GPUs. But it's interesting because still, even if we have low power and low consumption devices, we can still use these very small GPUs for acceleration of hyperspectral imaging algorithms. We have some papers demonstrating that the speed ups that can be achieved in these low cost and low power consumption GPUs can be very high, even if you need to find the right algorithm for the task. If the algorithm is not parallelizing well, then probably you need to resort to more sophisticated GPUs. But still, I believe some of the developments that are currently made, maybe Roberto can comment a little bit about that, at the European Space Agency and so on, are based on this kind of tiny but very, very low power consuming GPUs. And of course, you can also mount your own architecture. This is a very interesting development at the University of Las Palmas de Gran Canaria. They have, in Spain, they have integrated an UAV with a hyperspectral camera and a GPU for full onboard operation. The challenge here is, of course, in the energy consumption, which limits the autonomy of the system. But you can imagine the advantages that operating this kind of off-the-shelf system can provide. You can obtain a la carte flights, solve or address particular problems of your interest. And this is really the future, in my opinion, because the components, the hyperspectral camera, the GPUs are becoming smaller with more resolution, with less weight, less power consumption, and little by little we are getting close to the idea of commodity off-the-shelf remote sensing instruments, not only for space, but also for airborne applications. Okay, so other parallel processing strategies, I'm going to go quickly on this because we are running out of time. We are talking a lot about big data these days, so I believe hyperspectral is a kind of big data. It satisfies all the requirements and definitions of big data problems. So because we are referring to problems with volume, diversity, and complexity that require new architectures. So if we think about the 3 Bs of big data, volume, variety, and velocity, these are all satisfied by hyperspectral applications, which collect a lot of massive data sets with a large variety, for example, from the viewpoint of the available sensors. And also the velocity of the data is interesting because right now we have a kind of constellation of satellites, not only for hyperspectral, but also optical, multispectral, SAR, we have the Sentinels, we have the Gaufen 2020 in China. So there's really a high velocity of data that can be provided. And there is a fourth property that is related to the veracity of data that is always very important as it allows for the elimination of inconsistent or incomplete data. So if we think about these properties, the idea is how to exploit these big data problems using available architectures. We have somehow relied a lot on the MapReduce model. It's similar to the master-slave approach that I described in previous slides. And particularly with Hadoop and its variations, we developed some implementations of distributed algorithms. Hadoop is a tool that has several advantages. For example, the fact that we have an ecosystem of applications for distributed processing, and we have many different modules that we can exploit while developing our algorithms. But in terms of hyperspectral data exploitation, because of the memory requirements, we got better results with Spark. Spark was originally developed as a research project at the UC Berkeley. And the idea is to execute the jobs using processing batch that are ultimately faster than the MapReduce problem. And it allows for real-time data manipulation. So basically, we tend to see Spark as an optimized version of Hadoop in terms of memory exploitation. And this is very important for hyperspectral data applications. So I'm just showing you some results that we obtained for processing as compared to MPI. MPI is the standard of parallel processing, for example, in cluster computing. And you can see that the execution times for Spark in hyperspectral applications, particularly as the data becomes more massive, more high volume, can be better than MPI. So this is a very, very interesting observation, because we have a suite of tools and algorithms that are already in place by means of the Spark and Hadoop modules. And in addition, Spark provides optimized access to memory. So I highly recommend Spark as a solution for distributed and cloud computing of hyperspectral data, especially if you have data repositories that are distributed. Sometimes the hyperspectral data are not only in one location, but are distributed in different geographic locations. For example, ESA hyperspectral data is not always in the same ESA center. So we can take advantage of this distributed nature of repositories to perform also distributed data processing. And this is also related to the development of big data processing tools like Spark. Of course, deep learning is also a very important field, and there are many frameworks that you can use for this purpose. Deep learning is more like a black box in terms of algorithm development. We have conducted a study of deep learning tools and frameworks available, and we use the number of stars and the number of forks in GitHub repositories as a kind of indication to see which frameworks are more currently more widely used in different applications. And eventually we came up with a couple of conclusions. It seems that TensorFlow and Keras are the most widely used frameworks for deep learning. And also, if you look at the table in terms of APIs, Python is everywhere. So that's why for these new developments in terms of deep learning, also if you look at the number of GitHub stars and forks, tools and frameworks based on Python, such as TensorFlow or Keras, are currently dominating the wide spectrum of techniques that are available for deep learning. Once again, deep learning is providing very good results for hyperspectral. I have a kind of criticism for deep learning as compared to other techniques like a mixing, because in the end, deep learning is a black box. You really don't know what is going on inside, particularly from the physical point of view, while other applications like spectral and mixing are more physically driven and more consistent from the theory point of view. So this is just an open point for discussion. I know deep learning is everywhere. We are all doing deep learning, but somehow I think we are forgetting about other algorithms that can be applied in some cases. We don't need to resort always to a deep learning framework to solve a problem, not only in remote sensing, but also in other fields. So let me conclude the presentation with a quick case study, which is hyperspectral and mixing. We are going to see some algorithms and results. So the idea I already explained. In hyperspectral imaging, there are cases where the pixels are not completely pure. Because of the spatial resolution, we may have pixels that are made up of different pure spectral components, pure spectral signatures. That's what we call end members. So we may end up with mixed pixels like soil and rocks, vegetation and soil, even different kind of vegetations. Even if we think a pure pixel of water could be collected, maybe there is no completely pure pixel because there are mixing effects at non-linear level in the water. So it's a very difficult problem to solve, and it's not always related to the spatial resolution. because you could think, okay, with more spatial resolution, I can get rid of mixtures, but it's not always the case, as intimate mixtures are always there. Even in a 1 meter pixel or in a centimeter pixel, you can have minerals intimately mixed. So increasing the spatial resolution is not going to completely solve the problem of spectral unmixing. We have two main models for solving unmixing. One is the linear model, another one is the nonlinear one. The linear one is a simplification in which we assume the materials that contribute to the pixel in subpixel fashion, the three mixtures that we have in one pixel, are acting or behaving linearly in terms of reflecting the incident radiation coming from the sun. So in the sensor, we are observing a linear combination of these three end members that is weighted by the fractional coverage of the materials in the pixel. This is an oversimplification of real world, because in reality, as mentioned before, we have intimate mixtures. If we want to characterize intimate mixtures, we need to know the media parameters. We need to know the nonlinear function from which particles or on which particles are mixing. And that is very difficult because, for example, water behaves completely different from minerals or from vegetation. And we cannot have the knowledge about the nonlinear function in advance in many cases. In some studies, we have kind of mixed approaches, like a two-layer. For example, we have one layer with single scattering that would be similar to the linear model, and another layer that tries to mimic the nonlinear mixture, for example, in this case with vegetation. So that would be a possibility to have a mixed scenario. In reality, linear versus nonlinear has been a discussion for hyperspectral unmixing. And I would say 90% of the papers are based on the linear model because of its simplicity. There are some developments on nonlinear unmixing. And I would like to mention the work developed also on unmixing for removing the atmospheric interference, because in hyperspectral data, we have a problem with the clouds that normally you don't have with non-optical data like radar and so on. So there have been some efforts to use unmixing to remove clouds, in the sense that we consider that cloud can be an end member that is mixed with other materials, especially if the cloud is thin. And this particular end member could be removed to somehow see what is behind the cloud, and remove this end member to perform cloud remover with the unmixing itself. As I mentioned, the goal of linear unmixing, which is practically the dominant approach, although there are some new developments in linear unmixing recently, is how to find the spectrally pure components that you have in the data. If we think of hyperspectral data as a representation in 2 dimensions, that means that we are going to select only 2 bands of the hyperspectral data. The pure components, the end members, the pure pixels, will be located at the extremes of the simplex that enclose all the other data that are mixed in terms of the 3 basic end members. We can think about this as a color image. A color image has 3 end members, red, green, and blue. And all the other colors can be expressed as mixtures of these 3 basic colors. So this would be a good way to understand the concept of end member. The only thing is, in a hyperspectral data, we don't have 3 end members. We can have many more, and we have more bands than in a RGB image. So it's a challenge how to find the end members. And also, if the end members are properly found, and if we can really find pure pixels in the data, we can express all mixed pixels as a linear combination of the end members weighted by a given abundance fraction, which is the amount of the end member in each pixel of the data. This is a figure that I have extracted from one of the papers, one highly cited paper by the late great Professor José Manuel Biocastillas, who left us recently, and he was really the father of spectral unmixing. He made a lot of contributions in this field. We all feel very, very sad about the loss of José. He was a great person and a great human being. And his contributions will be, analyzed for for a long time in our remote sensing field, because he really introduced a lot of new algorithms, new techniques. He's really the father of all this spectral and mixing family of algorithms that I'm going to describe. And Jose created this wonderful figure in which he explained the step-by-step procedure to spectral unmixing. We can have some atmospheric correction and dimensionality reduction of the data, but then the key to unmixing is to use different algorithms, different techniques that can be related to sparse coding, sparse regression, or even finding the end members directly from the data and performing inversion. The outcome of unmixing is the set of end members, the set of spectral signatures that we have in the data, the pure components, and the abundance maps that explain how much of an end member is present in each pixel of the data. So in a way, it's a kind of enhanced classification in which we have for each pixel, not only one classification label, but we have the materials that participate in the pixel and how much of each material is present in each pixel of the data. So I'm going to describe an implementation of this full processing chain in a GPU so we can see some results. This hyperspectral and mixing chain has 3 steps. One is to estimate the number of end members. We need to know how many pure components are in the data. Another step is how to identify the spectral signatures of the end members. And finally, the abundance estimation, which is to find the coverage of each end member in the pixel. We have several techniques. For example, for estimating the number of end members, we have implemented the virtual dimensionality that uses the covariance and correlation matrix to determine how many pure components are contributing to the matrix. And in this way, we identify the number of end members. Another technique was designed by Professor Biucas and his student, Jose Nascimento, which performs a subspace projection approach to see how much data are comprised in the subspace and how much is noise in order to decide how many end members. It's a very successful technique without the need of any input parameters. For the end member identification, we use classic algorithms like mFinder. It finds the end members by maximizing the volume that can be formed by pixel vectors in the original data queue. It's similar to the concept I explained before. So we start with a random combination of pixels. We calculate the volume, and then we replace each pixel, trying all possible combinations. It's a combinatorial approach until we end up with the simplex with maximum volume. And the corners of this simplex are assumed to be the end members. Another algorithm is more trial and error, iterative error analysis. It performs a set of iterative reconstructions of the original image using linear unmixing until the reconstruction error is minimized. In this case, the iterative error analysis can also provide automatically the fractional abundances. And then for the abundance estimation, in the case we don't use iterative error analysis, we can use unconstrained least squares, which basically minimizes the reconstruction error after approximating each pixel in the original image, R, as a linear combination of the end members and the estimated abundances. So we minimize this error and we can obtain a least square solution in a simple way to find the fractional abundances. Optionally, we can impose the non-negativity and the sum to one constraints, which add a more physical flavor and coherence to the estimation. So we are going to use the hyperspectral data set that I mentioned before, the World Trade Center data. We have some ground truth, for example, the location of the thermal hotspots. And we are going to consider 4 different implementations for analyzing the performance of different algorithms in different platforms. We use a cluster, a heterogeneous network of workstations, an FPGA, and a GPU. And as you can see, we can estimate the area of the fires by using these 4 different implementations and compare to the ground truth area coverage of the different hotspots provided by USGS, which is the ground truth information in this particular case. You can see in the table that regardless of the parallel implementation that we use, we get similar estimates to the ones provided by USGS. Now, the goal, if we want to perform real time, is to process the data at the same time as the data is collected. So since this is average data, it is a push broom instrument that collects images in line by line fashion. We are are going to collect 512 lines in 5 seconds. This is the velocity in which AMERSIE collects data. So we are going to consider one image with 512 lines. This is approximately 140 megabytes of data every 5 seconds. Here you can see some of the abundance maps obtained from the data. This is the vegetation map. This is the smoke abundance map that you cannot see with the original image, but if you find the proper end member, you can see things that are not visible in advance. And then finally, you have also here the fire abundance map. These are the hotspots that we identified by looking at this fire end member. As you can see, it has very high radiance in the thermal part, meaning that these are hot pixels in the data, while vegetation and smoke behave in a completely different manner. We performed an implementation using a GPU, actually 2 different GPUs that are certified for onboard operation, Tesla and 580 GTX. And here we show the loading time, that means the time to transfer the data to the GPU, serial and GPU times. We calculate the speed up in both platforms. And we also provide the time in seconds for all the different algorithms that we are considering for estimating the number of end members, the signatures, and the abundances. You can see that the speed ups depend on the algorithm, but we can find chains that are performing in real time. For example, these 3 chains are below 5 seconds. So that means we can perform the full and mixing analysis, estimate the end members and the abundance maps in real time. For some other chains, we have almost real-time performance. That means we are not below 5 seconds, but we are close. All these algorithms have been implemented on NASA Web Coverage Processing Service, which is a cloud system for performing real-time or fast, in this case, a mixing of hyperspectral data. So this chain is already implemented in the WCPS interface that they have developed at NASA. And I also wanted to show some results for PPI, even if I'm running out of time. It will be very quick. The PPI is probably the most popular end member extraction algorithm. It's very simple. The idea is to run skewer projections to identify stream pixels in spectral space. So we run basically some random vectors that we project on all the pixels in the data. And those pixels that are repeatedly selected after the projections are considered to be the end members. So we developed an FPGA implementation because this algorithm is simple, and we managed to implement it in FPGA. Other algorithms we could not because of the difficulty associated to the implementation. And as you can see, we obtained some acceptable speed ups for most remote sensing applications. We also developed a GPU implementation. Here are the different modules for selection of the skewers, which are the partitioning vectors, the projections, the member selection, and the final unmixing. And we implemented this full processing chain in a cluster. As you can see, we could get a total performance time of 5 seconds, below 5 seconds, but we need 256 processors in the cluster. So this is not feasible for real time because the data need to be transmitted to the ground before being processed. In a heterogeneous network of workstations, we got a processing time of 83 seconds. This is a network of 16 processors that you can see here with different processing times. And here you can see the different communication links between group of processors. It's a very heterogeneous system. So it was a lot of effort to implement this code, and we couldn't get real-time performance. On the Xilinx Virtex 2, we also could not get real-time performance. Probably with a more advanced FPGA, we could do it because it really depends on the number of resources used. But this would sacrifice also the reconfigurability. So we had some issues on going further with this implementation. And finally, with the GPU, we could get almost real time. For 136 megabytes, we got a processing time of about 6 seconds. So our conclusion in general general, it's easier to get good performance with GPUs, and the coding effort is much lower than with other platforms, especially FPGAs. With the cluster, we could get good performance, but it needs coding in MPI. It's also more effort, in my opinion, than GPU, than CUDA. So in the end, in terms of programmability, the GPUs were really the most appealing platform. So in summary, if we compare the different architectures, of course, clusters are relevant for processing data already collected in repositories, transmitted to Earth, and is not easily adaptable to onboard processing. And we have some problems with maintenance and space requirement. We need air conditioning. We compromise mission payload if we use clusters for processing. GPUs are probably the best solution in terms of cost effectiveness because it's cheap, easy to program, low weight, but still it demands high power consumption compared to other solutions like FPGAs. And there's still some work to be done in terms of finding radiation hardened solutions for space-based applications, but we are currently on the way. And finally, FPGAs are currently the tool of choice for onboard processing. They have low weight and low power consumption. The advantage of reconfigurability, even if it comes at the expense of using more hardware resources to allow such reconfigurability, which limits the usage of the hardware. And it was difficult to obtain response in real time precisely because of this, because if we want to have full reconfigurability, we need to sacrifice part of the hardware to achieve this functionality, and then it's difficult to optimize the algorithms per se. So as a summary, regarding the different solutions that are available for HPC in hyperspectral image processing, I would say a very important question is whether we want to do onboard processing or not. If we don't need to do onboard processing, we can use standard solutions like clusters, multi-core heterogeneous systems, or even GPU clusters. But now if we want to go into the game of onboard processing, which is really the future of this field, a very important question is energy an issue. If we don't think we have problems with energy consumption, we can definitely go for GPU-based processing, particularly in airborne devices, because GPUs are very easy to program, and we don't care about the consumption in this scenario. However, if we are dealing with nanosatellites or UAVs, in this case, energy is probably a very important concern. So if energy is a concern, I would say another question to ask is programmability. How much time we can allow or afford in order to implement our algorithms. If we don't care about programmability, if we feel our algorithms are easy to implement, or we can sacrifice a lot of time to develop the algorithms, I would say FPGAs are the solution, particularly for spaceborne platforms, including satellites and nanosatellites, because FPGAs are currently still much more optimized than GPUs in terms of radiation tolerance and in terms of energy consumption. We can have very low power GPUs mounted on nanosatellites and still avoid compromising the mission payload and the overall success of the mission. Now, if we care about programmability, if we feel that the algorithms need to be carefully optimized, or we have some time constraints in order to port our algorithms, I would definitely recommend to look into low consumption GPUs like smartphones, like the ones in smartphones, and particularly because the radiation tolerance technology is now somehow being transferred from FPGAs to GPUs. Remember, I talked about the space cubes. They are now using the same technology for radiation hardening of FPGAs to put GPUs into space with the same reliance and with the same performance. So in the end, GPU is a much more easier hardware to program. And if we can have radiation tolerance and low power consumption, I believe we can see an explosion of implementations for GPUs in space, particularly because we have the reconfigurability program, the reconfigurability property is already de facto included in GPUs. So the threat for the future is to find the right balance between programmability and power consumption consumption and radiation tolerance, particularly in spaceborne missions. But we also have an opportunity, is the fact that specialized hardware evolves very quickly and the cost and energy consumption is dramatically decreasing. So I believe we are going to see many new advances in terms of GPUs or similar hardware to GPUs being used for real-time processing of hyperspectral and other kinds of remote sensing data. Okay, with this I conclude my tutorial. 5 minutes late, sorry about that. And I hope we can have some time for additional questions. I'm going to stop sharing the screen. And yeah, thank you so much for your attention. The floor is open to some discussion if Andrea considers appropriate.
Yeah, definitely. Antonio, thank you very much for your contribution. So definitely we can have some more minutes for some questions if they are coming up. I see that there are some showing up in the Q&A box.
Okay.
So
thanks, Adriano. Also, some of the mixing algorithms, the ones based on MCMC sampling, are quite a lot slower than, say, MFinder. Yeah, FCLS. They can still be deployed for real-time and mixing. What is the role in terms of application? Yeah, that's a very good question. I agree. I focus on simple algorithms that are easy to implement in GPUs. For example, MFinder, as Andreas mentioned, is very easy because we have a combinatorial problem. We just have a lot of vector products to conduct, but some other algorithms are more complicated, particularly those that try to include the spatial information. Sometimes we need to calculate superpixels or include the spatial windows or perform some kind of spatial pre-processing in advance to the spectral. And in this case, of course, the implementation in a GPU is better, is easier than implementation in FPGAs. But I would say all algorithms can benefit from the GPU, but some algorithms would benefit more than others. It depends on how much data dependence exists between the parallel threads when you design the algorithm. If your algorithm can work on a pixel level without many interactions, for example, between neighboring pixels, that algorithm is going to map very well in a GPU. However, if you have some kind of mechanism that involves communication between the pixels, it's very important to think carefully about how to avoid the communication, such communication, because even in a GPU, if we need to communicate a lot through the video memory, efficiency of the system. So the key aspect in GPU is try to keep low communication between threads and try to have the accesses to memories confined to the local shared memories in each multiprocessor. As soon as you abandon the local environment of the multiprocessor, there are going to be some data dependencies that are going to hamper the overall performance of the implementation. But you know, in our experience, we have seen very different speed ups. For MFinder PPI, it's easy to achieve very good speed ups because this is exactly the algorithm that the GPU expects. But for other algorithms, maybe the speed up is not so high, but still, in our experience, normally higher than those that can be achieved in FPGAs because of the complexity of the programming. I don't want to give the impression that FPGAs are so difficult to program. Maybe this is our experience or the fact that we always try to do it at the very low level. But I think today there are very interesting tools, very easy tools to develop automatic code in GPUs that we can take advantage in order to implement the algorithms in an efficient way. And then if you are interested in deep learning algorithms, maybe not for a mixing, but for classification, the good thing is that the frameworks already use GPUs in the bottom layer. So for example, if you use TensorFlow, this is automatically running the GPU if available. Of course, if you use CUDA, the efficiency of the algorithm will be much better because will be adapted to the algorithm, and it requires also a little little more effort, but the bottom line, what I'm trying to say is that the GPU can always help, more or less. But now, almost any development takes into account the GPU in terms of frameworks for deep learning, or even with MATLAB. Even if you're programming in MATLAB, you have a toolbox that can use the GPU in a very high level, in a simple way. But if you have a GPU, it can be used. So this kind of simplicity in the programming, I don't see with other platforms. And that's why I anticipate that the future for GPUs will be better than for other kind of high performance computing architectures.